Hello everyone and welcome. Today we are going to talk about static and dynamic properties of trajectories. This is a continuation of our section on molecular dynamics simulations. So let me share my screen with you and let's get started. This covers Haile chapters 6 and 7 on the static and dynamic properties. So we'll begin with an introduction. A static property is an inherent property of a system that does not change with time, whereas a dynamic property is a property of a system which does vary with time. We'll be looking at both of these types of properties over the course of today's lecture. There are various properties of a system that can be extracted from MD simulations, some of which are static and some of which are dynamic. So trajectories are going to provide us with the interactions between the particles and their surroundings. We want to keep in mind that our particles can have an interaction with the things that are close by and far away, and the way those are handled are slightly different. In particular, the electrostatic term, as we've talked about, is the one which is the long range that is very expensive to calculate, which is why we use the particle mesh Ewald summation to handle this. The short range interactions, that is the ones that are going to be within this radius here, will be handled in an explicit way, whereas the ones that are beyond that are going to be handled using just a generic screening correction term. So we have formulas for both the potential for the for the close contacts and also for the long range components. We'll be talking about the time averaging today. So the idea here is that over a simulation of time t, we may be able to average over that in order to determine some properties of interest. The question, of course, is always, is the time long enough? And what is that average value over that time? We'll be talking about whether or not taking a time average is the appropriate way to analyze your data and what this might say about the convergence of your system. Pressure is a quantity that we would be able to measure from molecular dynamic simulations. The pressure P is going to be related to the molecular quantities through the virial equation. We saw this last time. The virial equation of state. This virial equation is going to relate from the PV equals nRT, a familiar expression if you have taken any kind of physics classes. And the derivation of this is handled in Appendix B. It is a little bit long and drawn out, so it's really better handled in a physical chemistry class, but if you're interested in seeing it, it is there for you. The important things to take away from this are that this virial equation will tell us something about whether or not the system is behaving in an ideal way or not. So essentially what we do is we take PV equals nRT and we solve for V, right? So notice that we have here the rho KT. Okay, so the N is your number of particles. K is right here, which is typically the ideal gas law, R, you may know it as that, and rho is going to be the density being represented here. So typically this, so if you move all of the terms over to one side, we would expect that we could equal that equation to 1. And so, because basically all the terms would cancel each other out. And so what we can do then is we can look to see the non-ideality of this system by comparing what you get when you rearrange the ideal gas law equation with this actual equation here, and the difference that we get between between those is going to tell us something about the non-ideality of the system, which is what is going to be described by this, and that is the virial. So in static properties, we're not necessarily looking to see that the property itself is exactly static. We're looking to see that it's stable. So for example, here's the internal energy, the minus U. And so what we have here is that this value is fluctuating with very small oscillations around a mean value. So this is what we mean by when we say a static property, not that it exactly equals only one value, but just that it's fluctuating around a similar value. Here we also have the pressure. We see that again, the pressure is fluctuating. So we can we can control these things so that they do not get out of hand, because we can do things such as the coupling. This is variance in coupling to a temperature bath. And so what that will do is you do a thermal coupling so that the temperature will essentially stay the same, because you have an infinite heat, like a source of heat to keep everything the same. And so we apply these techniques in order to do the coupling of the system. And so by keeping the system at constant, under constant conditions, we have only minor fluctuations. So essentially, this is equilibrium dynamics, which is what we mean about a static property. So static properties are oftentimes used in molecular dynamics simulation, and in fact, I have some results from some research in my lab recently. This is the root mean squared fluctuation. This tells about the motion of an individual residue over the time of the simulation. And so what we're looking at here is the amount of fluctuation. This is a relative value, arbitrary units. And here what we have is the residue position. It happens to represent this protein up here. And so what we're seeing here is the variation in these by position. So this would be an example of another static property, something that we expect to be relatively the same once the system has equilibrated. We happen to be looking at traces here to compare between some various mutations in this protein system. Well, that brings us to the thermodynamic relationships, the thermodynamic response equations, which you may be familiar with from taking any thermodynamic classes or potentially some physics classes, are going to show how the thermodynamic properties relate to observables. The reason why we are interested in studying these is because these relate thermodynamic properties that are the state functions, the internal energy, the total energy, the delta G. These kinds of things are not things that we just have a thermometer to go out and measure. However, we may be very interested in studying these properties because they can tell us things such as whether or not a reaction will proceed or not. So what we can do then is we can write these thermodynamic response equations to show the relationship between some properties that are measurable with the thermodynamic equations. These come from taking the partial derivatives of the fundamental thermodynamic equations. So some of these measures that we are especially interested in are the heat capacity and the compressibility. The heat capacity is going to tell us how easily something will heat up. So for example, we may consider heating up two liquids and wonder which one will heat up faster, all else being equal. So one which heats up readily has a low heat capacity, and one which heats up and takes a long time will have a high heat capacity. So this one will both heat up and give off its heat readily, whereas the heat capacity of water, which is being shown here, this is much larger and it takes a long time to heat it up, but also means it will retain its heat for much longer time. This has to do with the intermolecular forces. So this, for example, may be perhaps an organic solvent or something of the like, which does not have strong intermolecular interactions, whereas water would have lots of intermolecular interactions. As a matter of fact, it has two hydrogen bonds, two hydrogens that can get donated to other waters, and two acceptor sites, each of the lone pairs on the oxygen. In the compressibility, we're usually thinking about how easily we can compress these different materials. We have a solid here, which is not going to be very compressible. Liquids are almost as incompressible as solids, and gases, on the other hand, are readily compressible. So when we study thermodynamics, we're almost certainly looking at gases. So here what we're taking a look at is the partial derivatives that can be taken in order to study these various processes. These aren't the only thermodynamic properties that could be studied. We do have a list of many others that could be studied. Perhaps you've heard of some of these, others of these may be unfamiliar to you. Some of these are interesting for people who are looking at material sciences. So for example, the volume expansivity or the Joule-Thomson coefficient. Sonic velocity has to do with the traversal of sound waves in various media. We've seen this one. This is a slightly different version of the compressibility. This is the isothermal variety. We also have the isobaric heat capacity, which is another variant on the heat capacity. So we do have a number of thermodynamic processes. And again, the point is to be able to connect these with observables that we're interested in studying. Entropy is another thermodynamic variable. This is equal to KLNW, where this omega is standing for the W. It means number of ways. And so this is going to tell us about the multiplicity of ways that something could happen in a system. More formally, the entropy is described using this thermodynamic relationship involving the energy, temperature, and change in volume and number of particles. Notice that mu is the chemical potential, N is the total number of particles, T is the temperature, V is the volume, and E is going to be the energy. So this suggests a variety of ways to study what the entropy of a system is. We could manipulate the system energy at fixed volume and number of particles. We could manipulate the volume at fixed energy and number of particles, and we could manipulate the number of molecules and at fixed energy and velocity. We can determine the temperature, pressure, or density dependence from simple thermodynamic properties and compute SA or G. These are the thermodynamic relationships, entropy, Helmholtz free energy, or Gibbs free energy by integrating the appropriate thermodynamic relationships as suggested by the equations we have seen. So this is just the definition of how we would do this, right? We would do the difference in entropy at two energies, and this is going to be the integration, and we can also do the difference in the temperatures, right? It's going to be equal to these thermodynamic equations. We can also take a look at the test particle method. The test particle method is the idea that we could change the number n of particles in a simulation. This typically tells us about the chemical potential. So the chemical potential is defined by the change in entropy per number of particles at constant E and V. And so what we're asking is, if we place this particle, how will the system be affected by that? That brings us to the radial distribution function. So the radial distribution function can be written in terms of the time steps n. So just call to mind that we have mentioned the radial distribution function earlier today. We have talked about that in terms of the distance of the particles from the particle of interest. And so what we may wish to look at is we may wish to look at a version of the radial distribution function, which is in fact going to calculate the number of particles as a function of the time steps. That is, this will be the time dependent version of this. And so what we can see is that we may get a different answer over time. This would be particularly interesting because the radial distribution function can be used in order to determine whether or not something has equilibrated. Remember that we talked about having the particles on a grid in order to begin with, and then that decayed over time. So we can use the radial distribution function as a function of time to see whether or not we have run the simulation sufficiently long such that that correlation from the position of the molecules on the grid has been lost, which is good because that means it's melted and now it's in the liquid phase. And so when we're running MD simulations, that's what we want, because we want to melt the water and have our protein just in a liquid. So this here shows us an example of what that would look like. This is the radial distribution function to differentiate between different lattice structures. So notice here that we have a couple of lattices being shown. We have the face-centered cubic lattice versus the simple cubic lattice. We are paying attention to the distance between the particles. Notice that this face-centered cubic lattice is less dense than the simple cubic lattice. And also notice that the distances that are observed between the particles tends to be different, and so they are able to be identified because of the spacing, right? The spacings are different. They both have some many particles at unit 1 away, because that is the unit of the closest packed neighbors. But then we'll have some substantial differences as we move out because of the distances between the particles as we move along. The radial distribution function can be used to differentiate between the liquid and the gas phase. Notice in the liquid phase we have an extra bump here, whereas in the gas phase we do not. Let's take a closer look at this curve shape and see if we can understand what's happening here. So what this says is that for particles having a distance less than 1.0, the population is extremely low because the energy would be exceedingly high. Therefore, the particles cannot be on top of each other no matter what phase they are in. In the low density gas phase, the particles basically mostly stick at a distance a little bit greater than 1.0, and then after that the interaction, well, so there is in a low density gas there's very little interaction, and so the particles spread out. However, in the liquid phase we have some interaction with the particles, the same as we do for the gas phase. However, most of the particles move away, and then here we see this resurgence of close neighbors because perhaps there is some interaction between those that is allowing them to stick together. This perhaps could represent a distance that would be for a hydrogen bond, for example. So many particles may be aligned at this distance because this is appropriate for hydrogen bonds. Gases lacking interaction would not have a preference for the atoms to come close together again, and so that is why we do not have the hump. Next, let's talk about time series analysis. So in time series analysis, we are trying to understand what is happening over time. Time series analysis accounts for the fact that data points taken over time may have an internal structure to them. So for example, there could be autocorrelation, some kind of a trend that happens, or some sort of a seasonal variation, and that should be accounted for. So let us consider this graph over here. This is some data about retail stores. And here the data has been averaged over all of them, meaning that it gives us this flat trend, whereas in fact, actually, sales could be going up over the years. And so by taking the average, this is not especially meaningful in projecting forward, whereas if we were to fit the data to capture this trend, that would be much more meaningful. We're aiming to find reasonable estimators to understand what trend is happening so that we can make a good representation of our data and perhaps estimate parameters from them, information like we've been discussing, or perhaps we want to project forward to see what would happen in the future. So one thing that we can use is we can use data smoothing. This is an example using a moving average. So in a moving average, what we do is we select some data point, and then we, instead of plotting the data just as it is, we're going to plot that data point as the average of itself and some data points nearby to it over some delta t. So here we see from the formula down here that we would look at some previous data points. In this case, we're going to select the delta t to be 3, so we use these 3 data points and average them together. And instead of plotting the individual raw data, we could plot the 3 and this data here. Then in the next case, we'd move up to the next value, and we would we would average over these and report. So this one would be averaged over these and reported, and then in number 5, we would do the look back on the past 3. So what we notice here is that the data that actually gets plotted in the moving average column here will encompass the values that had been used in the past. So you use the data more than one time, and of course it does reduce the number of data points that you have. However, the moving average may be a good way to normalize out some of the fluctuation that you may be seeing in your data. Next thing we'll talk about is the autocorrelation. So notice here that we have some data points. This in fact is a sine graph that has been modified by imposing some noise. We have randomly selected some numbers and added them or subtracted them from the sine graph to produce this graph over here. And the question is, would we be able to recover the original data? So the periodicity of a sine function is obscured by the random number multiplications in a process to remove that noise would be needed. The autocorrelation transformation may be able to do this transformation for us and can find that the dampened sine function is actually what is in here. So how could we understand this a little bit better? But before we delve into the mathematics of it, I think a useful thing to do is to look at our dynamic properties in terms of tape blocks. Of course, tape blocks are not in regular use for storing data today because we have things such as hard disks and USBs and many other things. However, tapes are still used in data centers for long-term backup. But nevertheless, even though it is an outdated explanation, it is very useful for understanding how our data is going to work. It explicitly shows data being represented as blocks, and what we can look at is how the moving average could actually work. So the idea is that we would have these various frames that we would look at, and we would have a delta t counted, calculated over some number of blocks in the tape. And so here what we see is we begin at the beginning and we average over these, and then we move up to the next. So this is our second calculation. And we see that this very much mirrors what we were showing in using the moving average of the data. So we can calculate whatever property of interest by doing exactly this. We can, of course, choose the delta t to be some other value. And in autocorrelation, we may actually, in fact, span several delta t's to find the one that works the best. The autocorrelation is simply just the Pearson correlation between values of the processes at different times as a function, or the 2 times of the lag time between them. So essentially what we're trying to do is we're asking questions that as we go over these various blocks of time, does the function look like itself in any other point in time? So for example, think back to a sine wave, the periodicity would match up, for example, the distance between the 2 maxima, which should be equal to the period between the 2 minima and so forth. So what we're trying to do is when we don't actually know what that distance is, ask the question if we could actually discover that. And so we can use the Pearson correlation between segments of the data in order to ask that question. So essentially what we're doing is we're checking for periodic behavior with itself. So let us allow the set x of t to be a random process and t be any point in time. X sub t is the value produced by a given run of the process at time t, and by that we mean calculation of the autocorrelation. So suppose that the process has a mean u sub t and a variance sigma squared for each t. Then we can use the definition of the autocorrelation function between any 2 times t1 and t2, and this is given by this equation here. This is the more general solution, and this x bar is actually representing the complex conjugate. We don't need to be quite so fancy because in MD simulations we are working in the real coordinate plane, so there's not a possibility to be in the imaginary, so we don't really need that. This is what the version that appears in your book will look like. So we see that we have the autocorrelation function taken at time 0, and then the autocorrelation taken at some delta t, t0 plus t. And we take the average of this, and this is defined as a of t0 minus t times a of t0. So we're going to look to see what this will look like. So autocorrelations for trajectories can be used, and the limit is the lag time becomes very small. Right, as the lag time becomes very small, this is going to simplify to simply just the static behavior. So there is in fact no lag time. And what we mean by the lag time is the time between those supposedly repeating positions, right? So we try a variety of different delta t's, and we're looking to see. But as we set that delta t to be very small, it's essentially the same as if we had looked at each of the points individually. However, the behavior is not periodic, then the correlation will not be preserved for large times. So you may have some correlation in the very beginning, but it's not really very pervasive. It's probably just noise. And so then what will happen is that your correlation will decay in time. You may also follow the decay of periodic conditions over time because that's interesting. So for example, watching the lattice particles move in time would be something that we could see that the autocorrelation function would show that perhaps there is correlation in the beginning for the positions of the particles. such as we also see from the radial distribution function, whereas over time we would see that that would dissipate, which indicates that our simulation dynamics has begun and that the equilibration phase has completed. And finally, we might be interested to normalize by the static correlation, just because that is a meaningful thing to which to compare it. Here's an example of autocorrelation with velocity. So this is a property of an individual particle and not the whole system. The autocorrelation between the initial position A0 and A of t is initially equal to the A squared, but as the time increases, it's going to decay. So this tells us that the correlation of the velocities initially may not be very diverse, but as the time increases, then we're going to decay into the Maxwellian dynamics. So again, from the kinetic gas theory, we see that the particles should be moving randomly with respect to each other when the system has become equilibrated. So the single particle version of velocity is going to be able to give rise to the temperature. So here we take a look at the summation over all the particles in the box. Each particle times its respective velocity, and that will give us the overall property of the temperature. This is a fundamental property of the kinetic gas theory. In addition, we may have space-time correlation. What we mean by this is the fact that correlation may be dependent on more than one property. So far, we've talked about the autocorrelation being correlated to the time. However, suppose it is also correlated on another factor which itself is also changing in time. So for example, we may have that the pressure is changing over time. So here we actually have a space-time correlation function being shown. Correlation may be dependent on time and another property which also varies, such as the local density, for example. So when we think about this, we can think about a little thought experiment. So imagine that you went to a train station and it's rush hour and Friday afternoon, 5 o'clock, and everybody wants to go home. How long will it take you to get from the entryway of the train station to the ticket counter and to the platform? Now you have 5 minutes before your train leaves. Will you be able to make it or not? So the idea here with the density is the density of the crowd may be varying over time. It's probably going to be reasonably dense, but for example, a train may pull into the station and many people pour off and get in your path, whereas another train might pull in and take a bunch of people out. People are constantly moving, so your progress through the station will be nonlinear. And so then we have this this concept of the correlation being dependent on the time, and also another property which is varying with time, which is that density. So this gives us the self-space-time correlation function, and that is being shown for 256 Leonard-Jones atoms here. And you see that we get a two-dimensional plot that shows how this works. All right, so that brings us to the end of today's talk about the time evolution and analysis of trajectory analysis. So we had an introduction today. We talked about the thermodynamic relationships to use those properties which we can measure in order to pull out the properties of interest that are the thermodynamic variables. We also talked about the radial distribution function. So the radial distribution function is useful for understanding whether or not the system has reached equilibrium or not. And we also talked about the time series analysis, the methods we discussed, word smoothing, and the autocorrelation. So I hope you found this enlightening to understand a little bit more about how we can analyze the data that we get from molecular dynamics simulations, and as a matter of fact, for many other kinds of simulations as well. Thanks so much, and we'll see you next time. Bye-bye.